Good morning, everyone. Welcome to Essentium's live webinar series. In this time of physical distancing, we sincerely hope that you and your family are safe and healthy, and we're honored that you'd spend some time with us here this morning or this afternoon. We have people on the webinar from all over the world. So today's webinar is titled How Additive Manufacturing Benefits Aerospace. We'll be doing a deep dive into tooling, jigs, and fixture applications for the aerospace industry. This webinar is going to be recorded, and we will be sending it out to everyone who is on the email list after the webinar. So the agenda for our time, we're going to be talking about a little bit about Essentium. We'll give an overview of who we are. Then we'll talk about the production platform that we've built for the aerospace industry. And then we'll talk about our material set, our high performance material set. And then we'll talk about applications at the end. And then at the end, we will have a time for Q&A. So if you have questions, please feel free to leave those questions in the chat bar, which you can find at the top of your Zoom webinar information. So if you have questions, please leave your question in the chat bar there. Introduction's sake, my name is Josh Lawson. I am head of sales at Essentium, and I'll be your host for today's webinar. Also joining us is Erik Gjovik. Erik is Essentium's chief product officer and co-founder, as well as Brandon Sweeney, who is Essentium's head of R&D and co-founder. For bio's sake, Erik is the chief product officer and co-founder of Essentium. Erik brings a wealth of experience in engineering, manufacturing, and operations, spanning diverse industries such as consumer electronics, aerospace, robotics, and semiconductors, with companies like Mophie, Apple, and Orthodyne, to name just a few. Brandon Sweeney is the head of research and development and co-founder at Essentium. In his role, Brandon has been instrumental in researching the bleeding edge material science needed to bring Essentium's 3D printing technology to life. So good morning, guys. Hope you're doing great out there.
Good morning, Josh.
Good morning. Good morning, Brandon. I think you're on mute, but so just there we go.
Okay.
Perfect. Good morning. As we get started, just wanted to give everyone a brief overview of who Essentium is. So Essentium is in the extrusion space. Our headquarters are in Austin, Texas, but we have operations around the globe in Europe and Asia. We are building and manufacturing extrusion printers. We have a full set of printers that we've developed over the past few years. And then we manufacture multi-layer filament. So that's our specialty. We manufacture all different types of filament, but multi-layer is one of our specialties, which Brandon will talk about in a little bit. We've also been able to partner with some of the largest manufacturers in the world, as you can see there on the screen. And really what we've tried to do is allow them to be successful as they are trying to change how they are manufacturing products around the world. So as we get started, I wanted to show you just a quick video of what we've been able to accomplish specifically in the aerospace industry with our aerospace customers.
The pain points in the aerospace and defense industry are many. Antiquated supply chains, parts that are no longer in stock, airplanes that are very old. Additive manufacturing is uniquely positioned to address all of those aspects. We see this in the commercial sector of aviation, but we also see it in the governmental sector of aviation. Aerospace and defense has to innovate, but some of the challenges around that have a lot to do with the regulation and the certification pathways. But this is where the opportunities exist for additive manufacturing, which is a challenge, but 3D printing is up to that challenge. Essentium is committed to solving the most demanding problems in the aerospace and defense industry. We're working with advanced materials, the world's fastest extrusion machines, comprehensive software suite that provides an open ecosystem that delivers the freedom to innovate and full control into the customer's hands. These materials and these machines combine together to create a total solution at the lowest cost and at the highest speeds of anywhere in the industry. And this type of technology is ready for the aerospace and defense industry.
Because the HSC has speed and scale, we are able to operate at the speed of relevant. We are able to print at the speed of relevant. We are able to produce materials at the speed of relevant. So you can be printing jigs, fixtures, toolings, anything really, instead of going out and looking at the supply chain to provide that for you. A platform like the HSC that has both scale and speed can keep the warfighter ready, because if something needs to be tailored or changed out in the field, it can quickly be done, and then the mission continues.
So we had a customer who was in a production environment that was running 24/7. One day that production line went down. So that customer would have spent tens of thousands of dollars to have that part manufactured, would have lost millions of dollars with that line being down. But with our machine, they're able to take that design, put it into a 3D printed format, print it, and within an hour, they had that production line back up and running. For us, when we combine the cost of our machine, the speed of our machine, and the efficiency of the materials themselves, it creates a great ROI opportunity for our customers that is much less than our competitors.
We're focused on making sure that our customers gain an advantage and that our customers are successful in ways that traditionally were not seen as possible with legacy technologies. The aerospace industry is really looking for new solutions in 3D printing, and Essentium's up to the challenge.
Okay, perfect. Well, to get started, I wanted to bring in Erik to specifically talk about our platform that we've developed. And Erik, as we're getting started, one of the things that you and your team have been focusing in on is not just building a printer, but building an entire platform. So maybe for our audience out there, what does it mean to build a platform for the aerospace industry?
So we started looking at the various portions of making a product. So the machine, the process, and materials. And we looked at each of these with the aim of creating an industrial production machine. It can be used for prototyping very effectively, but we were looking at the machine that I wanted for my use as a manufacturing engineer, as a supply-based engineer in industry. And I never found what I wanted. So we went back to first principles. So as we looked at what the machine had to be, it had to have a certain speed, it had to have a certain price point to meet the economics of scalability. The process had to run fast. It also had to be an open process. The materials, you had to have a selection of materials. In fact, you have to have an open materials platform. We think it's very important that there is a strong materials element to an additive manufacturing company, because that's what the parts become. The materials and the process create the part, and that's very important for us. And combining those two capabilities is very important for us. But one thing we noticed with each of these, to be a true industrial machine, you had to be open. So when we mean open, the machine itself, it's an open G-code platform, very similar to the G-codes that Ultimaker or the open source machines use. We're not using some proprietary language for the machine. G-code, you should be able to understand it. Machinists will not be afraid of this G-code. They should be able to look at it and understand it. The other thing is the process has to be open. So we don't hide any of the capability of our machines. And the third thing is materials are also open. So we are backed by BASF, as you may recall, but BASF is totally fine with us working with other suppliers of materials. And you can use whatever material you want in our machine. We think our materials have some huge advantages, but again, it's an open materials platform because our competitors are open platform as well. Our competitors are, FANUC mills, DMGs, Haas, those type of machines are open. You don't have to go to FANUC and say, hey, I want more FANUC aluminum. So those are our competitors, so we had to be open as well.
Yeah, so through the years, you've been in a lot of different manufacturing environments. Some of the most well-known brands in the world, you helped bring some of their products to the customers around the world. So when you were in that previous life, looking at manufacturing, and you looked at additive, what were some of the things that you saw that were missing?
Um, One big thing, scalability. So we work very hard to make our product scale, and you do that with a couple things. One, the machine cost has to be reasonable. It can't be a multi-million-dollar machine. It also has to be fast enough. The speed reduces the cost of each part. So there's a barrier to entry there. And then the third thing is the materials can't be proprietary. They can't be 3 times market price. Market price materials, a fast machine that is not overpriced, is the key to opening up that ecosystem and opening up scalability for manufacturing. So as we've gone forward, that has been our primary aim, is to keep the economics and keep the return on investment, what we're able to give the customers, so that they can have a reason to buy more machines and go into mass production. So we feel that we're in a very good position right now to offer something that hasn't really been offered into the industrial market, which is a mass production ready additive machine tool.
Yeah, so if you see the chart on the screen, where 3D printing previously was prototypes, visual prototypes, and maybe some production. But as you get into higher speeds, higher scale, it allows you to go further up that chain into mass production. So maybe talk a little bit about the machine itself, and how you built the machine, kind of taken back from your semiconductor days.
So it's funny because our team is from the semiconductor industry. We worked together years ago at a company called Orthodyne that was later bought by Kulik and Sofa. And we built very high speed machines. So looking at this machine, if you've seen a pick and place machine in the semiconductor industry, you're going to see something you recognize. So several things that are different from other machines is, one, it's a different process. It's built around the process itself, which is high speed extrusion. It's not FDM. So for those reasons, this thing is built to be extremely fast and responsive. So to do that, it's a full digital servo linear motion XY stage. Because of that, we only have 10 moving parts, and 6 of those are long life bearings. The other thing that makes it, an industrial machine as well, is the feedback. So just like in the semiconductor industry, in-process feedback is very important. So we have multiple channels of feedback, and that allows you, one, to develop processes faster, but also understand the part you're building and have a digital fingerprint of that part to make sure that the part is built correctly. The third thing is the entire machine is built for responsiveness. So it's a large machine. It's 690, 500, 600 millimeters, pretty large build area, but we can get across that entire XY stage in a third of a second. So if you're used to FDM where you have to do retracts, we don't do retracts. And that not only improves our process, it improves part strength as well. And Brandon can go into that a little bit later. So the entire machine is built around some responsiveness. We have there is no brass in our feed chain for the filament itself. So there's no lead getting the filament. So it's, an FDA safe type of machine. The other thing is the nozzle itself has a sapphire tip for life, because at our speeds, brass would last under an hour, hardened steel will last 8 hours. So we have to have a hard sapphire tip. What's interesting is our nozzle, to respond to our process, it's not like a normal FDM nozzle where it takes 30 seconds to get the temperature. We can go from room temperature to 550 degrees C in a couple seconds. And we can drop temperature and raise temperature as we're printing. It's a live parameter you can control. So there's a lot of things that went into this machine that makes it both be able to support the high-speed extrusion process, but also be an industrial machine. And several of those things are IR heat. So we do not use a traditional oven. We use infrared multi-mode heating. So we're heating the part, not the chamber. So we don't have to wait for the chamber to heat up. That's a huge advantage for us. It also makes it easier to change parts out because you're not sticking your hand into a 200°C environment in the chamber. The part itself is hot, but the chamber itself isn't that hot. The other thing that's very good for us is, we come from I've owned CNCs that were certified for Boeing. And so things like being able to run a Renishaw ball bar test on this machine with the G54 codes so that you can calibrate and certify a machine for production. We can also roll back the firmware to previous versions if you certified on a previous version of software. We also are not going to change the software for every material that comes out. So we're not going to charge you when new materials come out to run those. And like I said, you can run any material. So the machine itself is highly reliable. There's very few moving parts, and it's relatively easy to service with the electronics in panels and front and back. So we've gone through everything we can think of to make this fit into an industrial environment, survive in an industrial environment, and make sense to industrial users.
Great. Yeah. So, I know a lot of our customers who are on the webinar today, they're thinking, okay, what does this actually mean for me? So if they've been using a legacy additive platform, what's going to be some of the biggest differences that they're going to experience from one of those legacy platforms to an Essentium HSE?
The big one is that you're not going to be shocked on how to program it. It's not an entirely different system as far as programming is concerned. So if you've worked on let's say an Ultimaker or an open source machine, you're not going to be totally shocked. So it's not like an entirely different process, but in the end, the speed you have is significant. It makes it applicable to projects you had never had the chance to use before. So also the range of materials, the ability to do everything from simple PLAs to high-end peaks on the same machine at speeds that are unheard of is probably the biggest change. I think the biggest change you really see is there are times when you can print a part faster than you can design it. So we've had cases where we've had, relatively complex clamps and things, and someone designed it, they put the part in, go to lunch, come back, and it's done. Those kind of things change the way you use the machine. So I think that's the most surprising thing. It changes the way you look at the availability of a three-dimensional part.
Sure. Great. Yeah. So the next slide, it talks a little bit about one of our customers' parts that we've worked with. Maybe talk about how speed really does impact the production process for a customer like this.
Well, for a customer like this, this particular customer has thousands of fixtures, and they have a business that used to have 17 products and now has like 17,000 products, and they run in smaller and smaller quantities. They change fast. So doing fixtures for this, and this is a small holding fixture, small, like 5 by 7 inch. And for them, they were sending stuff out to make. So the cost was far reduced from what they're doing, and the speed was increased. So this is one of the few times where the ROIs are so strong, and it's strong for, quite frankly, any, even an FDM technology. The ROIs are usually 80% return, 80% improvement in cost and time. But the difference here is you can scale. So this particular customer prints, several hundred fixtures a week. And they're starting out, they have one machine and they're printing lots of fixtures. So they're successful now, but they have a reason to expand because they can scale. So the big difference here is the cost and time and scalability. So you see a lot of our competitors do a white paper on building a fixture and how much they save, but you have to ask them, how long would it take to do 1,000 fixtures? And for us, we have a good answer for that. And because of the cost of the machine and the speed, you can scale it.
Yeah. Yeah. I think back to our early days, and, we would come in and say, okay, how long would it take for us to build 10,000 fixtures, 1,000 fixtures, 15,000 fixtures? Because that's what true manufacturing is working on. And that's what you were working on back in the day, and why you didn't use additive at scale,
yeah.
because there was not a good answer for you back then. Right.
Yeah. I mean, we would bring up a line with 800 and some fixtures at a time, and it just was not possible to use additive. There was no, you just couldn't afford to do it, and you didn't have the time.
Great. Yeah, so as we've talked about the platform itself, part of the key with a platform like that is not just the ability to move fast, but actually to extrude materials. And so many of our customers and partners don't actually know, but we started out as a materials first company. So we started out working with some of the largest manufacturers in the world, working on their toughest material issues. So what I want to do next is transition to Brandon to talk about the materials that we've developed specifically for aerospace and what he and his team have been able to accomplish there.
Well, thanks, Josh. As Josh mentioned, we're going to go through kind of our material portfolio as it pertains to the aerospace industry, and discuss some of the applications that each of these materials has. And, hopefully this can spark some new ideas on when you actually have materials that are very high performance and beyond, kind of the standard palette that's been available in FDM. There's a lot of new opportunities that are available in this space. So if you get anything out of this today, hopefully it's new ideas for how FDM, and in this case, HSC 3D printing can work on your factory floor. You can go to the next slide. Yep. Oh, I'm in control. Okay, so we're going to go through materials based on their properties. So in aerospace, we're really going to look at mechanical properties, temperature performance, things like chemical resistance, and then extra functional properties in order to define, first of all, where is this material going to be used? What is the proper material to select for a given application? Because that's what guides us to the process of understanding, these are the properties I need, and I want to do that at the lowest price point so that I can get to scale. If I'm going to print 1,000 fixtures, PEEK may be a good choice. It may work for your application, but there could also be a lot of other options out there for lower cost materials that achieve the same functional properties, and that allows you to scale at a much lower price point. So one thing I wanted to highlight in terms of when you start out with a given application, usually the first thing an engineer is going to look at is the mechanical strength of the parts. So the strength and the stiffness, and using that to guide, what is my end use application? How am I going to design this part to withstand the forces involved when I'm, functionally making a component that has to survive? And really, we like to have a lot of data when we go through these decisions with customers. And I wanted to highlight here that Altem 985, really cool material, highly applicable for the aerospace industry. My background, I worked for the Army Research Labs for a little while, and I did some 3D printing for functional prototypes. And ABS is what we got to work with when we were just kind of playing around with stuff and trying to get an idea of how it would work. If we actually wanted to make something functional, the one material that we had to work with was Altem 985, because it was considered, the top of the pyramid in terms of performance and strength and durability and toughness, and kind of a good blend of all these properties. And that was based on, the portfolio of materials that we had available to us. But I wanted to highlight the fact that, if you expand with an open materials platform, there's a lot of other things out there that push beyond Altem 985. There's materials, composite materials that have carbon fiber or glass fiber reinforcements that can really push you to the next level in terms of the strength and stiffness that you have available to work with to make lightweight fixtures that are very functional. Another thing that I wanted to highlight here is that, when you consider strength, it's not just kind of the base strength of the polymer itself. You have to consider that additive manufacturing is a process in and of itself. Just like injection molding. When I injection mold parts, I have to consider, where my flow gates are. Do I have any weld lines? Is there an orientation effect because of how the material was injected into the mold? additive manufacturing has some of the same constraints. You have to understand that, we are flowing the polymer as we're depositing it. And there's an orientation effect that's often seen. And I think this is one of the things that I hear the most often is that, I can't trust my 3D printed parts because, they have terrible interlayer strength. And that can be true. And it's certainly something that you have to consider when designing for these parts. But one thing that we've seen with the HSC that's really, really interesting is that since we extrude at such a faster speed than other platforms that are out there on the market, it kind of opens up new possibilities in terms of increasing your interlayer bonding. The degree to which, 2 layers of material deposited onto each other are going to bond and fully weld together has a lot to do with the thermal history. So as I start to print faster and faster, I get closer and closer to an isothermal process, which really gives me a big boost in my mechanical properties in between the layers. So this is we did a round robin study looking at things like the nozzle size, speed, nozzle temperature, chamber IR settings that we applied. We also compared it to some plaques that we printed in the Z direction on a Stratasys platform. We had a partner that printed us some specimens. And up here in the top left-hand corner, I have a comparison between XY properties. So for all 1095 printed in the direction of the tensile strain, we were seeing about 78 megapascals for strength. So you get a little bit of an orientation effect there. So good strength. In the Z direction, what was surprising to us is that we were seeing up to about 63 megapascals in the Z direction. And for comparison, when we pulled the specimens that were printed with the exact same settings in terms of the nozzle diameter and the size of the tower that we printed to route the Z dog bones out of, the Stratasys specimens were pulling in the mid to high 40 megapascal range, which is quite a bit lower. And also what I don't have on here, but I can share data, is the standard deviations were quite a bit higher on the Stratasys platform because it has to pause and do some wipes and come back over and try to restart again. And with the HSC, we don't have to do those kinds of things. We just get to blow right through the part at 300 millimeters per second for this particular print, and saw some really incredible values. And then even if we go to larger nozzle diameters, so if you're printing really big parts and if you can get away with using a 0.8 nozzle, we've seen values in the low 70s, and they were very tight standard deviations on those parts. So bigger nozzles, there's a lot more residual heat that's coming through into the part as you're printing it. And we see, again, increased layer bonding. So that, I just wanted to highlight that really quickly is there's some unexpected gains that are to be had when you're printing faster and things that are not normally seen with an FDM type system. So moving into kind of advanced materials, another thing that we've been innovating on, as Josh mentioned, is kind of the next generation of additive materials and additive composites. So we've created a technique on our production lines here to be able to create multi-layer filament where we can deposit multiple layers, core shell, into a filament structure when we actually produce the filament. And one of the cool things that's allowed us to do is to create materials that normally were not even possible to turn into filament. So we started to work with very highly loaded carbon fiber reinforced polymers. So when you get to above 20 or 30% carbon fiber, if you're using long fiber, aerospace grade materials and a pretty stiff matrix for it to go into where there's good compatibility between the fiber and the polymer, it becomes really difficult to turn that into a filament. It becomes very brittle. And when we tried just extruding it as a monofilament, we couldn't even wind it onto a spool because it just snaps. So we used our multi-layer extrusion technology. And the reason why I have a picture of sausage on here is you could imagine that sausage, ground beef in the core, doesn't really have any mechanical integrity. But if you put a really, really thin casing of a tough material on the outside, it encapsulates everything and contains it so that it's actually packageable. It has integrity. So we do the exact same thing for filament. We put a thin, tough casing of the same polymer on the outside of the filament that encapsulates the highly loaded core. And this really opens up an entire new possibility for composite materials. And again, I'll say the HSE is uniquely suited to print with these kind of materials. They can be fairly abrasive to brass nozzles, and the HSE has a sapphire tip that is going to have an extremely long life when working with these kind of materials. It's not going to blow out or change dimensions or alter as you're printing parts. And one thing I want to highlight when it comes to composite materials, they can be surprising. There's some unexpected results when you have to consider things like strength to weight ratio. So we see, not only for parts that need to fly on a plane, because that's where you typically think about strength to weight ratio, but even stuff like fixturing. So if I'm going to have a worker, manually raising up a large fixture to hold something in place or orient a part for a process, or if they have to hold it manually for a long period of time, you want that fixture to be really lightweight and strong. And, you can't just consider the strength of the material that you're using because it's the true metric that you want to take into account is the strength to weight ratio. Same thing for robotic end effectors and robotic fixturing. Those systems, anytime you're moving stuff around really fast on a robotic arm, you don't really want to have a whole lot of mass on the end of that robotic fixture. As you have more mass, it starts to get more difficult to control the kinematics of that system. So you want to have strong, lightweight materials. And our material, the HTN CF25, it actually has better strength to weight ratio than 304 stainless steel by a long shot. And then even 6061 T6, not T0, the annealed state. This is like the fully hardened 6061 T6 state. We beat that strength to weight ratio. And that's pretty cool. Being able to have a material that is outside of the capabilities of metals that we currently use for fixturing applications when it comes to kind of those metrics. Another thing that I want to highlight as an additional functional property that we'd like to consider is temperature performance. So this is that same material, the HTN with 25% carbon fiber. And this is a video that we made showing how it's pretty crazy, but this is lead-free solder. And we created a crucible and melted the solder inside of this printed part. And this was just a demonstration to show that, if I'm working with soldering fixtures or things that are going to go through an SMT oven, materials like this can survive those temperatures. You don't necessarily need PEEK or some exotic high temperature polymers in order to survive these kinds of temperatures. The carbon fiber actually increases the thermal resistance, the heat deflection temperature, and the continuous operating temperature of this material. And we can do this for multiple material chemistries as well. So, as we go up the pyramid in terms of performance, that's going to give us higher and higher temperature resistance to various processes. And we designed the HSC to be able to handle everything from the bottom of the pyramid to the top of the pyramid. And of course, as you get to more and more exotic applications for aerospace, if you need extreme chemical resistance or extreme temperature resistance for an application, that is pushing you up to the peaks. But we always want to make sure that we're using data and the informed decision process to decide what is the right material selection. We don't want to over specify a material because then we're paying too much, and you could be using additive more effectively if you use the right material for the right application. So we have a lot of data to go with materials that we work with commonly, and this really helps us with customers to identify, is this part going to be exposed to this temperature for thousands of hours? Is it just going to go through a paint oven for a couple minutes? These are the kinds of questions that we typically ask to identify what's the right material chemistry for an application. So of course, on the extreme end of things, you've got your peaks and PECs reinforced with carbon fiber. These materials have incredible temperature resistance, very high glass transition temperature. But then again, I'm going to highlight here All-Time 985. It's definitely a high temperature polymer. It is amorphous. So as soon as you go over the TG, it pretty much loses most of its mechanical properties. So there's actually quite a few materials in here, like the HTN CF25, that can have higher temperature performance for a given application because it has that carbon fiber reinforcement in there. And then PPS, this is another really interesting material to us. It's called the poor man's PEEK. So PPS carbon fiber is much lower cost even than your peaks and PECs, but it gets you very close to the mechanical properties and the temperature resistance for certain applications. So that might be a material, if you were interested in PEEK but can't afford it, there may be an option that's going to get you close enough to really scale an application. So this is an example. I wanted to highlight the difference between amorphous and semi-crystalline polymers. These materials, the ABS and the PPS, have the exact same glass transition temperature. So you can't just use TG to define the temperature resistance of a material. Because the PPS is semi-crystalline, it's going to have an operating temperature and a heat deflection temperature well above the ABS, even though its TG is the same. So you can't just look at one number. You have to know, what is the true parameter that I'm interested in for an application so that I choose the right material. And one of the interesting things is that historically, almost all of the materials that were available for material extrusion 3D printing were amorphous, or they were semi-crystalline with a very low crystallinity level. So they're basically amorphous. And as soon as you get into semi-crystalline polymers, there's some very interesting properties that you can open up and access. For instance, chemical resistance. So one of the applications that I'm going to share is paint scrapers. And it sounds kind of silly, why wouldn't I just injection mold a paint scraper? There's a good reason. But if I look at the chemical resistance between All-Time 985 and PEEK in dichloromethane, which is a common ingredient in paint stripper, no contest. This is over a period of an hour or so. And the All-Time 985, which is an amorphous polymer, completely dissolves, whereas the PEEK is basically completely unaffected. So that's just one example of how you need to consider not only the mechanical properties, but what is the actual end use application? Is this part going to get covered in paint stripper? And that is a very aggressive compound that's going to come in contact with my part. I need to choose the right material for that. Another thing that it comes up all the time in aerospace is the flame retardancy. So looking at FAR 25853 flammability and flame smoke toxicity requirements for materials. And a lot of polymers have inherent flame retardancy. Of course, All-Time 985 passes these kinds of tests. PEEK, PEC, PPS, and a handful of others are also commonly considered to pass these tests. Just based on their chemical makeup, they're inherently not going to combust or release very toxic gases if they come into contact with flames. Some other chemistries, they can be made flame retardant with some additive packages. So there's some interesting materials that are coming online from various manufacturers. I've seen some polycarbonate and some polyamides that are going to pass FST requirements for the aerospace industry. So we're interested to, start working with some of those. But that is, something to consider is, is this part either going to be in an area where it could combust as a jig or a fixture or a tool, or, is the intended use to go on the airplane itself as an aircraft interior or some component, and does it need to pass these kinds of tests? And again, as an example, this is just a quick flame test between ABS and PEEK. Blowtorch on each. ABS is not going to pass these tests. It's a great functional prototyping material, for low temperature, room temperature jigs and fixtures. But if I need flame retardancy, go with peak, all-temp, something that's rated for this kind of application. And Essentium, we're working on certification standards for our materials. We've kind of have two avenues going. One of them with the FAA and NIAR. So looking at the next steps for getting some of these other materials like PEAK, PEC, certified on the HSE platform for airworthy parts. One of the other materials that I want to highlight here, this is based on our portfolio of functional multi-layer filaments, is ESD safe materials. So materials that have inherent electrical conductivity that make them static dissipative. And we create a multi-layer filament structure. We put carbon nanotubes on the outside, and this makes them pass very common standards for low charging and static dissipative environments. So this is important for things like jigs and fixtures, going into electronics manufacturing and assembly, a lot of electronics on aircraft systems, caps and covers for connectors in aerospace structures, to make sure that you're not statically charging or damaging electrical components on an aircraft. Another thing is for flammability. So if I'm making a component that's going to be near a fuel system or next to your fueling lines, you have to have ESD safe properties there so you don't create a spark that could potentially cause an explosion or some other fire event. With those materials, one of the cool functional properties with our ESD safe materials is that the coating that we put on the outside that makes them electrically conductive is very high quality. Other manufacturers add a lot of carbon black or graphite to make the material conductive. We don't do that. We have very high quality additives that are non-marking and non-marring, so they won't rub off onto things like circuit boards or components that are being assembled on a factory floor. One last class of materials that I kind of wanted to bring up was TPU and elastomers. So if you need parts that are going to get smashed, banged, dropped, squished, or if you need to isolate some vibrations, a lot of vibrations on an aircraft system, we love TPU. Thermoplastic elastomers and urethane chemistry is incredibly tough. We have different durometers. We even have a material that's on its way to being FST certified. It passes the flammability requirements, and we're doing additional testing to see if it's rated for the smoke and toxicity as well. But there's a lot of materials that are not tough that are 3D printable. But if you really have an application where it's going to get banged around a lot, we suggest TPUs all the time. They also have excellent chemical resistance and high and low temperature resistance as well. So we're going to kind of transition into some applications now, and we'll try to go quickly through this. But here's a few kind of applications for example parts that we've printed in conjunction with the United States Air Force. And the first one is a thread protector for a C-130 landing gear. So as you take the wheel off, you have to put this thread protector on so that you don't mash up the threads on the wheel. Very simple part, but it was a custom machined part out of steel. And they actually said, we're looking for something that's a little bit more lightweight. We also want to redesign the thread portion of the system because right now it takes 2 guys to install this thing, and we'd like it to be a one-man job. So we were able to print this in an hour and a half. And this is actually a better material choice for this application. If you do drop the wheel on that lug protector, they were saying that even though it's supposed to protect the threads, if you have a metal and metal contact, that could still damage and mar those fine pitch threads. They really wanted something that was a little bit more compliant and durable, so that if they did kind of mash it on there, that you weren't going to have a metal on metal contact. Another example is an engine intake cap. So when we looked at this part, we decided that because it was in contact with degreasers and transmission fluid, the HTN, the high temperature nylon in our portfolio, was the right material choice because it withstands the chemical resistance needed for that application. And the interesting thing about this part is that this particular transmission, it was missing an engine cap, and it was pretty much just sitting there, couldn't be shipped out until they had that cover in place. So the procurement for that could take anywhere between 6 to 12 weeks, just through normal supply chains, because this is a really hard to find part, and it's not easy to make. So we 3D printed one in a matter of 2.5 hours, and just being able to put that cover on there and, you know, bolt it in place, that allows you to ship this part out and get it to where it needs to go, and saves you, you know, weeks of time for something that's pretty trivial. Another application that I mentioned before was paint scrapers. So there are so many different kinds of paint scrapers, different geometries, different tools that they have to interface with for maintenance and repair of aircraft systems. And again, they're going to come in contact with solvents, potentially, you know, really aggressive stuff that's designed to remove putties and paints. So we selected HTN CF25 for this particular paint scraper because it also needed to have a good amount of stiffness. We were trying to replicate the feel of a phenolic part. And the reason why they wanted to 3D print these is because they had been machining these out of phenolic sheets, but recently there's been some new regulations that prohibit the machining of phenolic components on bases just because of EHS concerns, breathing in glass fiber machine dust. And if you could 3D print these structures that are kind of, you know, there's probably 500 different shapes and styles and curvatures that they put on these things that have the chemical resistance and the strength and the stiffness that's needed, then you can really shore up your supply chain and be self-sufficient to produce the parts that you need, and, you know, stay away from the regulations of inhalation risks. The final one was a wheel chock. So we mentioned TPUs for their ability to be super tough and durable. And again, you'd say a wheel chock, why not just, you know, buy that off the shelf? It's a really simple part. And you would think so, but some supply chains and procurement channels can be very convoluted and difficult to work with. So to get a wheel chock like this could still take a matter of weeks. And as a safety protocol, you know, every single vehicle that's in a hangar or out on a line has to have a wheel chock on it, so they can get written up if they don't have these in place, and they can get lost or damaged or, you know, misplaced. And being able to print this overnight, so you could, you know, I need a wheel chock. Okay, normally you'd have to go through your procurement system, and maybe the part itself is not that expensive, but the shipping could be really expensive. The shipping could be more than the cost of the actual wheel chock itself. And if I went through a normal procurement chain, that could be, you know, 3 weeks, 4 weeks, if things are moving smoothly, if I have funding. But if I have a variety of materials that are very agile, and if I have filament that's on a shelf that can be turned into anything, the limitation is my imagination. And if I have a part on file for a wheel chock, then if I need a wheel chock, I start the print before I leave for work that night. And the next morning I have it. It's sitting there on the bed, ready to go. And I didn't have to go through any of my normal supply chains or procurement channels. And, you know, it just gets you back up and running so much faster. So when you have functional materials, when you have materials that are able to meet the demands of each given application, it's really going to free up the design creativity and the number of applications that you have access to. Something that I wanted to also highlight here was verticals. So we look at how to use materials based on the verticals that they go into. And the HSE right now, some of our target verticals are tooling, injection mold tooling, thermoform tooling. So we have materials that withstand the pressures and the temperatures that are used for these kind of applications. And we have a lot of examples of how we've been able to create tools for that industry. jigs and fixtures. So the assembly and manufacturing, maintenance, repair, overhaul of aerospace systems involves a huge number of tooling and fixtures and components that aid in the process of actually getting that system up in the air. And we have a wide variety of materials that are going to meet every single one of those applications. A few others are orthotics and prosthetics. And casting. So this is another application for us, is working with the casting industry for investment casting or lost foam or sand casting, and making tools for that. Now I don't have it on here because it's kind of an emerging application for us. And we are looking into the next steps for becoming aerospace certified for some of the materials that we print on the HSC platform. But we are definitely looking into creating end-use parts that are airworthy and certified. And an example that I actually have right here with me in the room, Josh, if you can throw me on the full screen here. I just wanted to share this really quickly because it kind of shows the next steps and the direction that we're taking for large parts that are printed out of Altem 985. So this is actually an avionics cooling duct. And these things, this is actually probably a medium-sized one for this industry. So these things can get really big, but you'll notice just kind of the scale of this part. This was printed on the HSC, and this was actually done with a 0.8 nozzle. So instead of a 0.4 with a 0.8, because this doesn't have a whole lot of really fine features to it, it allows us to go quite a bit faster. And also it's going to be stronger in comparison to a 0.4 nozzle. But you'll notice that this has a beautiful surface finish. We're able to print super fast on this. The layer bonding is going to be incredible. And this is a very functional part that could save thousands of dollars and countless hours of custom manufacturing. These types of components are typically made with a composite layup technique. And being able to 3D print stuff like this is game changing for the aerospace industry, especially if you have an aging aircraft where it's difficult to find the right parts and components. What if the supplier doesn't even want to make it for you anymore? But if you have the file on hand and you can validate that it's 3D printable with aerospace certified materials, and that you're getting really tight tolerances in terms of dimensional accuracy and the mechanical strength of this part, this can be an airworthy part. So wanted to really highlight that application because we've seen a lot of interest for avionics cooling ducts, components inside of an aircraft structure that are totally 3D printable. And that's absolutely on our radar. So,
and Brandon, that's Altem 985, correct?
Correct. Altem 985. Essentium is manufacturing and extruding filament ourselves here. We also work with Gjovik to supply filament from them as well. We're working on AS 9100 certification and ISO 9001 and getting the materials that we produce here aerospace certified so that if you buy filament from us, you're going to have the data and all the certifications in hand to be able to produce parts and know that this is backed with an aerospace grade stamp on the material.
Perfect. Thanks, Brandon. Thanks, Erik, for deep diving in there with us. So for all of our participants, if you do have a question, we're about to go into a Q&A time here to end our time. If you do have a question, please leave it in the comments or in the chat part of the webinar, and I will start going through those here in the next few minutes. But before we do that, Erik, if you want to just touch on tooling or mold tooling specifically, I think that was one of the applications that we were looking at that I wanted you to make sure and highlight.
Yeah, so we've done quite a bit of work on with a particular automotive customer to make injection molding tools. So, molds that actually fit on a full injection molding machine, not a low pressure machine with 100 PSI coolant. We have some technologies that seals off the mold with conformal cooling. We're getting many shots out of these molds. It's not like we're, running 3 or 4 shots. We're looking into the hundreds. We're going to go beyond that. The interesting thing is the parts themselves are pretty much indistinguishable from, soft aluminum, like quick molds. And they're shooting regular like PP, glass fiber, some abrasive materials into those, and they do fast fills. And the test we've done a while ago, some people have seen this part at some of our trade shows, and when we're able to do those, the parts themselves you could put right into a car. It's pretty interesting. So we're making advancements there. People are starting to look at printing slides, actually printed slides, complex motion in dies, and looking at bigger sizes. So, and that's a great place. It saves both money and time. It's a good bridge to manufacturing. And quite frankly, with the costing of the process, you could actually just do it in production, replace the molds when they're needed and bring up new molds. So it's a very good alternative to bring up molds very quickly to match very agile production requirements. And we see things, the pressure to go fast, to release product quickly is very intense in the consumer electronics industry, but it's heading to other industries as well. So we really look at some of these offerings as allowing us to offer an extreme agility and responsiveness to manufacturing customers.
Perfect. We're actually getting a few questions about that specific application. One of them is about surface finish and the type of surface finish that you can expect to come off of a mold like that.
So generally the molds, we'll print them and then they'll go into a CNC for the Class A finishes. The texturing companies, the ones that use lasers, we haven't done a whole lot of texturing because most of the unless, Brandon, correct me if I'm wrong, most of them have not had textures. They've been gloss molds or something was going to be coated. But I don't really, to me right now, I don't see any issues with a texturing company that uses lasers would not have a whole lot of issue texturing our dies.
Okay, great. Yeah, another question was about certification. So Erik, you mentioned this a little bit on how you built the machine to be certification ready. They asked, can you go back to that and talk about that a little bit more?
So unlike some of our competitors, we're not going to force you to upgrade software to bring on new materials. So that's one. The second thing is I actually have built a machine that was certified by Toyota, which is rather difficult, by the way. And so all the lessons we learned there 20 years ago, we're putting into this machine. So things like multiple channels of data we're collecting for the machine. We actually can create a data package for each part. So that can become part of the qualification. The other thing is when you develop the process to qualify a part, you have all that data available to you. We're not hiding anything from the user. So one, getting the data to create a qualified part and also using that data for in-process inspection is very important. So both of those, the machine is fully capable of doing. The second thing is qualifying the machine itself. So you need to qualify the materials, which is, Brandon's group, and in aerospace, we're working through the aerospace qualifications now, but also the process. So you have to have machine, materials, and process all certified and traceable. So on the machine itself, we have diagnostics in the machine to make sure the machine is running correctly. We can use Renishaw ball bar test. I've tried it. It's interesting. But you can, there are ways to certify a machine that if you've certified a CNC machine for aerospace, especially for like a Boeing style qualification, you should be able to do use most of those tools to qualify. And then because it's an additive machine, we have some added benefits. We can at any time throw in a couple coupons while we're printing. So that's a very standard practice, even sometimes in injection molding, to have a sacrificial coupon. But those kind of things that you do now are totally available and easy to do with an additive machine, especially ours.
Okay, perfect. Last question was about the high temperature nylon material that Brandon, you had talked about. How does that compare to other nylon carbon fiber materials that are on the market currently?
Mhm. So, we've seen some nylon carbon fiber materials that use nylon 12 as a matrix, or nylon 6. Some of them use highly milled carbon fiber, so the carbon fiber is chopped up almost into powder, and not really a fiber anymore. And that's done, they choose either a very soft matrix or very short fibers in order to get around that whole embrittlement issue and the filamentizing issue. And it yields materials that can be tough, and they print really nice and they look pretty. But when you really go in and you compare the strength and the stiffness, um, it can be 100 megapascals off of what we've been pulling on some of our dog bones. And the reason again is our high temperature nylon, which in fact we formulated in partnership with Lehman and Voss. So these guys, they know materials at the compounding level, and we worked with them to formulate this specifically for 3D printing. And it incorporates a high temperature nylon copolymer. So it withstands higher temperatures than any normal nylon matrix. It has better chemical resistance. And then the other thing is that it has better compatibility between the resin and the fiber. So they interact better together. And all those things combined just give it this really great overall performance compared to other stuff that we've seen in the marketplace.
And it is one of my favorite materials, and it prints beautifully. It's a tremendous material. I mean, this is kind of like the black aluminum that I've always wanted. So, I would definitely check it out. It's a brilliant material. And one thing I want to say Brandon hasn't said is we have our own injection molding machine. So when we test against molded properties, we actually can mold our dog bones. So, that level of detail that Brandon's group goes through to make sure the materials are exactly what we say they're going to be, and test them. We have a really strong materials team. We are a materials company, and we take that very seriously. So we really invite you to, really look into the materials we have and work with Brandon's team. What is interesting, there's so many really outstanding materials coming out. You really have to come back and look periodically, see what we have, because we're making advancements, every couple of months. So just keep checking back. What we can do today is not going to be what we do tomorrow. It's going to really do some really nice things coming up.
Okay, perfect. One of the questions was about how do you identify aerospace parts that are suitable for 3D printing, and specifically extrusion. So, Brandon, maybe give a high-level overview of what that looked like for one of our aerospace customers to identify the parts that would work.
I think a good place to start, at least a safe way to start, is to identify materials that are already produced that are thermoplastic. So, go into any aircraft system and look around you. And there's a lot of stuff that's made with polymers in there because they have great lightweight properties, and they can be mass produced a lot faster than metal can via injection molding or thermoforming. So if the component is already produced with a thermoplastic, that's a great way to identify, hey, maybe I could make this with a 3D printing process, and maybe I can adapt the design for additive. If something was thermoformed or injection molded, you could probably get the same form and function of the part, but just adapt it for 3D printing. And potentially you could make it even more lightweight, so you can save on material than if it were produced with other methods too. So I'd say that's a good place to start. And it doesn't even have to be components that have, a beautiful surface finish that are customer facing. It could be stuff that's kind of hidden, brackets or hinge components that pretty much no one ever sees, that are produced with high performance thermoplastics now. And those are great candidates for 3D printing.
And pretty much every tool and fixture is a candidate as well. And also think about the molding. If it is injection molding and it has to be injection molding, think about making the mold itself. with an additive technology to save money there. And especially for parts that are end of life, or, we talk about, it's hard to get some parts. I mean, some of the parts in the Air Force, the companies don't even exist anymore. So they really do have to sometimes go and remanufacture, re-engineer parts. There are systems available on the market that will look through part libraries and kind of pick out ones that are suitable for printing. Some of them are quite good. So I don't have if you ever go to any of the conferences, there are generally a couple of companies that have those kind of systems. And if you have a large part database, it's not a bad place to start.
Yep, absolutely. Okay, guys. Hey, thanks so much for your time this morning, and to all of our attendees out there, thank you for being a part. We're honored that you'd spend some of your time with us. If you do have more questions, you can send them into sales@essentium3d.com or info@essentium3d.com. For more information, you can visit our website, essentium3d.com, or you can follow us on Facebook, Twitter, whatever other social site you go to. So thanks again, stay safe, and we hope you all have a great day. Thanks for being a part.
Thanks, everyone.
Take care. Bye.
Bye.